All right, class, welcome to the video for Math 1030, Unit 6D on statistical inference. We're going to begin by thinking about the typical coin experiment. We toss a coin 100 times. What happens if the number of heads was 53? What can we say about the coin? Well, we would assume that the coin is fair, and the result would be around 50 heads or 50 tails. The difference is getting the 53 heads instead of 50 is attributed to chance. Okay, so it's not going to be exactly the same. Okay. So that's what we would assume. So we would assume the coin is fair. And the result would be 50 heads and 50 tails. The difference in getting $53 heads instead of 50 is attributed to chance. Okay. What if the number of heads was 20? We would assume something significant has happened to the coin, so it would only give 20 heads instead of 50. So it's not fair. Okay, so something significant. So let me put that back in there so that's important. Something significant has happened to the coin. And that's the important part. So what is significant? That's the key. And we're going to specify that and call it statistical significance. What is statistical significance? Well, a set of measures or observations in a statistical study is said to be statistically significant if it is unlikely to have occurred by chance. Okay. Said measurements or observations in a statistical study is said to be statistically significant. If it is unlikely to have occurred by chance. Okay. Are the following events statistically significant? So let's take a look. The team with the worst win-loss record wins one game against the team with the best record. Okay, so this is where the book starts out, and even though since there is a really bad losing streak on the worst team and a really good winning streak on the best team, that something significant might have happened to have the worst team lose. Well, even worst teams win sometimes, and so that could be against anybody. Could even be against the best team, and they might not have had a good day. So this relationship is not statistically significant. Here's one that's a contrast. 16 of the 17 hottest years in recorded weather history since 1880 were from 2001 to 2016. Okay? So because that's the hottest years in the most recent times, something must have happened. Okay? Something significant. And that's what has spawned these global warming or climate change type ideas, okay, to come. Okay, so scientists have been investigating that for many years. Number 3, a change in a poll with a random sample of 1,000 people from 51% support the president one week and 49% support the president the next week. Has something significantly happened to make that decrease by just 2%? Well, because the decrease was small, and it might be it's likely attributed to chance, where a random sample of 1,000 people thought 51% support the president, and out of another random sample of 1,000 people, only 49 did. So the feeling about the president hasn't changed too much, and we attribute that small difference to chance. Okay? So it's not statistically significant. What happens if we take this poll, when you do a random sample from 1,000 people one week, 70%, and then the next week, only 30% support the president? So has something changed? Well, yeah, likely. Something has changed. something significant has changed. And the president must have done something to have such a dip in support. A researcher conducts a double-blind experiment on whether or not an herbal remedy is effective in preventing colds. 100 people were in the treatment group, and 100 people were in the control group. 30 people in the treatment group ended up with colds, while 32 people in the control group ended up with colds. Okay? So the treatment group had 2 people less end up with colds than in the control group. So the difference is very small, and so likely the difference is attributed by chance, and the herbal remedy didn't really have an effect. So we say it's not significant. So such a small difference between the treatment group and control group is attributed to chance. And not the remedy. Okay, so the researcher constructs the same experiment, and out of the 100 people in the treatment group and the 100 people in the control group, 22 people in the treatment group ended up with colds, and 34 people in the control group ended up with colds. So we have the kind of the same situation, but kind of maybe with a different remedy. Okay, so there are a number of less people getting colds in the treatment group. And so we can say, well, that's probably significant. So it's probably statistically significant, but how are we going to know for sure? So statisticians have quantified significance at these certain levels. Okay. So first level they researched or established was the 0.05 level. Now 0.05 is the same as 5%. Is the same as is the same as 5%, which is equal to 5 out of 100, which is equal to 1 out of 20. Okay. So 1 out of 20. Statistical significance at the 0.05 level means that 1 in 20, or 5%, of the possible trials is attributed to chance. meaning that 19 out of 20 results came because something significant was happening. Okay. Significance at the 0.01 level, which means 0.01, which is equal to 1%, which is equal to 1 out of 100. Okay. Means that 1 in 100, or 1%, of the possible trials is attributed to chance. In 99 out of 100, results came because something significant is happening. And you notice that only 1%, 1 out of 100, is attributed to chance. 1 out of 100 the results. So it is very, very possible that something significant is going on or affecting whatever phenomenon you're studying. So let's go back to the herbal remedy. Okay. If the herbal remedy experiment was conducted 100 times, and one case showed a difference in the treatment group from the control group by chance, and the other did not, the other 99 did not, then we can conclude there is strong evidence that something significant is at work, and it'll be the remedy. So before we had 22 people in the treatment group for this remedy idea, end up with colds, and 34 people in the control group ended up with colds. So more people in the treatment group who had the remedy, the herbal remedy, did not end up with colds. So what we're saying is that if there is 1 out of 100, if the significance level is 0.01, then there's strong evidence that the actual difference in the people from the treatment group compared to the control group was the herbal remedy. Okay, so if the herbal remedy experiment was conducted 100 times, and one case showed a difference in the treatment group from the control group by chance and the other 99 did not, then we can conclude there's strong evidence that something significant is at work. And it's the remedy. Okay. In 1954, Dr. Jonas Salk conducted an experiment on whether or not his polio vaccine was effective in preventing polio in children. 200,000 children were in the treatment group, and 200,000 were in the control group. 33 contracted polio in the treatment group, and 115 contracted polio in the control group. Calculations show that the difference between the groups, occurring by chance, is less than 0.01. What can we reasonably conclude? That less than one case in 100 showed improvement by chance. Showed improvement by chance. Not just improvement, but prevention. No improvement, we can say. Okay, we can conclude that less than one case in 100 showed improvement by chance, which is strong evidence that the vaccine had a significant influence. On preventing polio. Okay, great. Moving on to number 4, we were talking about margin of error and confidence intervals. What is margin of error? Well, margin of error helps us understand how well the sample statistic is likely to approximate the true parameter. Okay? It is a margin or a range of how accurate. Okay? So it helps us understand how well the sample statistic is likely to approximate the true population parameter. Okay, and so what we have is, here's an example. Oh, first we're going to do confidence interval. The confidence interval is the range where the true population parameter lies based on the sample statistic. So it's the confidence interval is the range where the true population parameter lies based on the sample statistic. Okay. Now here's an example of, I'm going to zoom in here on this blank space here and talk about the margin of error and the confidence interval. Okay, so we have this range of percents from 0 to 100. Okay. And for an example of maybe something like unemployment, we'll have a sample statistic of 5%. We asked a bunch of people about their job status, and 5% said that they did not have a job in our sample. Okay, so I'm gonna maybe change the color here. Green. So this is not drawn to scale, but okay. So we have our sample statistic there. And so our margin of error is, say, 2% or something. Okay, so if we know that the margin of error is 2%, this will help us build our confidence interval. Okay, so our confidence interval is on either side, 2% on either side of the sample statistic. And so we have right here and right here. So this right here makes up the confidence interval. This will be 3% because it's 2 less than 5%. This one will be 7% because it's 2 more than 5%. Okay? So that's our confidence interval. And in that confidence interval lies the true population parameter, okay, or what we want to know about the population. In part C, we're going to kind of take a side step to just kind of discuss like how should we set up a study. So we have 1,500 students at a school, and we want to survey them to know what percent are satisfied with their education. What is a good way to conduct the survey? Okay. So one good way is to try and find a sample. You want to sample using a random sample. So we'll use a random sample. And select 25 students. And to ask them the questions. Here we have a diagram that says that, okay, with 95% confidence interval, right here, that the true population parameter lies within the range of each of the trials for a random sample. So if we note that all of these lines here are the confidence intervals, sample statistic. Okay, so here's our sample statistic. Same thing with their sample statistic, and then they calculate the margin of error. Advance that, and so on. But note here that this is where the 1 out of the 20 samples does not contain the true population parameter, but all of the rest do. They all span in here. Okay, so this is a true population parameter. They all span it. Okay. Now, the margin of error at the 95% confidence level means that we are 95% sure that the true population parameter lies within our sample confidence interval around our sample. And so to know how far above and below the sample statistic to go, we use our margin of error. And in the book, they describe the whole derivation of the margin of error. I won't describe that into the handout, but I will give you the formula that it results that 1 over the square root of n, okay, where n is equal to the sample size will give us the percent below and percent above, where we can say with 95% certainty the true population parameter lies within that interval. So we want to find the margin of error in the confidence interval in these examples. Okay, so a survey of 500 people finds that 52% plan to vote for Smith for governor. Okay, so we're finding A, the margin of error, and B, the confidence interval. Okay, so first we're going to look at the margin of error. The margin of error formula says that we just do 1 over the square root of the sample size, which is 500 people. Okay, and when we do that calculation, we get approximately 0.045, which is equal to 4.5%. Okay, so once we calculate the margin of error, we will know that how much our confidence interval will be with 95% certainty, that the true population parameter lies within it. Okay, so we'll find that. So if I take my 52% and subtract 4.5%, I get 47.5%. And then if I take my 4.5% and add it to the sample statistic of 52%, we will get 56.5%. Okay, so within 47.5% and 56.5%, that's the percent of people that will vote for Smith. Now, because majority rules, Smith is not a shoo-in here for winning the vote, because if he gets 48% of the vote and his opponent gets 52%, then his opponent will win. Okay. Let's go to the next one. A survey of 1,500 people finds that 87% support stricter penalties for child abuse. Okay, so I'm guessing that this statistic is real. It's from the book. We're going to increase our sample size to 1,500 people. Okay, in the other study, there was 500 people. And if you notice the difference, let's take a look at what our margin of error will be. And we'll compare it with our last one. So 1 over the square root of 1,500 is about equal to 0.023. Which is equal to 2.3%. Okay. So our confidence interval is 2.3% above 87% and 2.3% below 87%. So 2.3% below 87% is 84.7% to 89.3%. So those are my confidence intervals. Okay, our next example says, the Bureau of Labor Statistics surveyed 60,000 people and finds that 3,420 are unemployed. What percent of the sample are unemployed? So here's part A. And what percent, here's B, of the population is unemployed at the 95% confidence level? Okay, so what we need to find first is this, what percent of the sample are unemployed? Okay, that's our sample statistic. So we're going to calculate that to be 3420 over divided by 60,000, which is equal to 0.057, which is equal to 5.7%. Okay, so for the sample statistic, people in the sample, only 5%, almost 6% of them don't have jobs or unemployed. Okay, so that's our first question. What percent of the sample are unemployed? What percent of the population is unemployed due to a 95% confidence level? So we need to calculate the margin of error. Margin error is 1 over 60,000, which is equal to 0.004. Okay, which is equal to 0.4%. Okay. And with that margin error, we're going to take it and apply it to the confidence interval. Okay, so we're going to take our 5.7, subtract 0.4%, and we'll get 5.3%. And we'll take that 0.4% and add it to 5.7%, and we get 6.1%. Okay, so the unemployment level is 5.3% to 6.1%. We know that the actual statistic for the total population is in there. The population parameter is in that interval with 95% confidence. Okay, next we have hypothesis testing. So in order to give an example of what this idea is, we're going to take a look at what this product gender choice means. Okay, so gender choice was a real product that, when taken, claimed to have increased the chances of having a girl from the normal chance of about 50%. So in an experiment, if the product does not work, we would expect that the percent of girls to be born to a sample of women to be about 50%. Okay, so that's like the normal. If the product does work, we would expect the percent of girls born to a sample of women to be significantly more than 50%. Okay, and that significance would be attributed to gender choice if it passes the significance test. All right, so when we do studies in experiments, the scientists create a null hypothesis and an alternate hypothesis. Okay, null hypothesis, alternate hypothesis. The null hypothesis is what normally happens. Gender choice does not work, and percent of girls born to women is about 50%, like normal. Okay, that's our null hypothesis. The alternate is the one that favors the product under study or things like that. So gender choice does work, and the percent of girls born to the sample is significantly more than 50%. Okay, and what we mean by significantly right here is that we say statistically significantly. Okay, so we're going to try this idea of null hypothesis and alternate hypothesis with the next few examples. For example, a college president claims that the 6-year graduation rate at her college, four-year college, is higher than the national average of 60%. So 6-year graduation rate means that the student took 6 years to graduate. Okay, and so this college has a high percentage of those who graduate because it's higher than the national average. So it's pretty high. So the null hypothesis, if we're to study this in depth, is to say that the 6-year, assume the normal, that the 6-year graduation rate at her college is not higher than the national average, but just the national average of 60%. Okay? So the null hypothesis is the more normal situation. And what our experiment does is it tests something that is different than normal, some sort of significant interaction. Okay, so the 6-year graduation rate is 60%. We're going to assume that that is in line with the national average. The alternate hypothesis, which is like our claim, contained in the claim, is what the college president is saying, that the 6-year graduation rate at her four-year college is higher than the national average. Okay, so the 6-year graduation rate is greater than 60%. That's the alternate. Okay. Let's take a look at the next example. The governor claims that the median high school teacher salary in her state is above the national median of $57,900. Okay, so the null hypothesis again is what is more normal. Okay. Which is the median salary, the median high school teacher salary, that is, at her school, okay? So the hypothesis is more the normal hypothesis. And in this case, it is the median high school teacher salary is, like everywhere else, the national median, $57,900. Now, the claim, which will become our alternate hypothesis, is exactly what the governor claims. Okay, the median high school salary is greater than $57,900. Okay, next one, another practice for formulating the null hypothesis and the alternate hypothesis. The FAA claims that the percentage of flights delayed more than 15 minutes at the Denver airport is greater than the national average of 15%. Okay, so the null hypothesis is more than normal, and we would say that the percent of delayed flights is 15%. Okay. And then the alternate hypothesis is what the claim follows. the percent of delayed flights is greater than 15%. Okay. So when we come to the outcomes of hypothesis testing, okay, we have our null hypothesis and we have our alternate hypothesis. After we collect data from the study or the experiment, we can either reject the null hypothesis or do not reject the null hypothesis. Okay? And we think about why can't we just accept the null hypothesis? Now, let's say that our in-flight experiment has a sample where the percent of delayed flights is greater than 15%. Okay. So in the flights experiments, if we see if the flights are delayed, more than 15%, okay. So it's greater than 15%. The claim is being followed. We see that with our evidence. We say 15% maybe at the 0.01 level, for example. We say we reject a null hypothesis. And accept the alternate. Okay. So with the flights experiment, we tested how many flights were, what the percent of delayed flights were. We found that it was greater than 15%. And so we do our significance testing, calculation, and we find that the flights are significantly delayed at greater than 15% at the 0.01 level. We are going to then say that we reject the null hypothesis and accept the alternate. Now in part number 2, in the flights experiment, if we see flights delayed more than 15% or more than 15% delayed, In the flights experiment, if we see that greater than 50% are delayed, but the significance is greater than 0.01, then 0.01. Or greater than 0.05. We say we fail to reject the null hypothesis. Okay, which means that we don't have enough evidence or significance to accept the alternate hypothesis. So all we do is fail to reject the null hypothesis. So why can't we just accept the null hypothesis? Okay, and just say we say fail to reject or do not reject. Well, we can't just accept the null hypothesis as true because there could be other reasons besides our experiment that could give the reason that the null hypothesis is not true. Okay. We just can't accept the null hypothesis as true. Because there could be other reasons besides our experiment that could give reason for the hypothesis that the null hypothesis is not true. Okay, so we're going to go ahead and do an example here for number 7. For a hypothesis test, we need to do, for that kind of a decision, if the results are statistically significant at the 0.01 level, the chance difference is less than 1 in 100, there is strong evidence that for rejecting the null hypothesis. Okay. If the results are significant at the 0.05 level, the chance difference is less than 1 in 20, there is moderate evidence for rejecting the null hypothesis. If the results point to a chance difference greater than 1 in 20, the result is not statistically significant, and there's nothing significant going on, and there is not sufficient evidence to reject the null hypothesis. So we do not reject the null hypothesis, or we call it failing to reject the null hypothesis. Okay. So we have our experiment, and we'll go ahead and do this for cars, and we'll talk about that. The owner of a car rental company claims that the mean annual mileage for the population of all cars in his fleet is more than 11,000 725 miles, which is the mean for all cars in the United States. A random sample of 225 cars from his fleet has the mean annual average mileage of 12,000 miles. Assuming the mean annual mileage for all cars in his fleet is 11,725 miles, the likelihood of selecting a random sample with a mean annual mileage of 12,000 miles or more is 0.01. Okay. So what is the null hypothesis? Remember that was like kind of the normal thing here. Normal and then claim. Okay. So what is the normal thing? That the cars in his fleet follow the national average of 11,725 miles per year. So it's a null hypothesis. Okay, so what's the alternate? Well, the alternate follows what his claim is. The null is what usually happens. The alternate is what follows his claim. The cars in his fleet do not follow the national average and average more than 11,000 miles a year. Okay, so that's what the alternate is. From the evidence that his sample had statistical significance of 0.01, meaning that the mean annual mileage of the sample is greater than the national mean of 11,725. Okay, from that evidence, should we reject or not reject the null hypothesis, and why? Okay, so the significance level is what's important here. The significance level that the mean of the sample is 12,000 miles is 0.01, which means that we have strong evidence only one case in 100 is attributed to chance, So we have strong evidence to reject the null hypothesis. And accept the alternate. Okay, that's our handout video. Please let me know if you have any questions.